Okay, YouTube, in this video we're going to look at another linear programming situation that is being applied here to a real-world context. And so how we kind of set this up, our objective function and constraints, and how we find our feasible region and test our points. So let's go ahead and start with this, reading through the problem here, kind of mentally highlighting important values. So it says the liquid portion of a diet is to provide 300 calories, 36 units of vitamin A, and 90 units of vitamin C. And what I want to do is make a little amendment here. We say it's to provide this much right here. I'm going to make a little note here. We say at least, we need at least this much in our diet. Okay. So we say a cup of dietary drink X costs this much money and provides this many calories, this many units of vitamin A, and this many units of vitamin C. I'm going to not underline those yet here, but we say a cup of dietary drink Y costs 15 cents per cup, provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. It says how many cups of each drink should be consumed each day to obtain an optimal cost and still meet the daily requirements. So where it says optimal cost, let's go ahead and start with our objective function and our variables here. It says how many cups of each drink and optimal cost. So first things first, in terms of our variables, let's go ahead and start with this. We say let X equal the number of, and we're just going to say cups of drink X. And then of course Y would be the number of cups of drink Y. I suppose the idea would be that we're trying to get an optimal cost. When we talk about an optimal cost, we're really trying to find the minimum cost. And so if our job is to minimize the cost, let's come up with an objective function that we're trying to minimize here. So our objective function, since it's cost, I'm going to write cost equals or C equals, and obtain my cost. What I know is this. We know that it costs 12 cents per every cup of X and 15 cents per every cup of Y. So we could say that basically 12 cents times the number of cups of that plus 15 cents, 15 cents times the number of cups of this would give us our overall cost. And this is what we're trying to make as small as possible in this problem. So let's go ahead and start talking about our constraints then. So now as far as constraints are concerned, one thing that I want you to get used to is when we talk about application problems, we should always put in these constraints for the most part, because we're going to deal with non-negative values. We're going to be in the first quadrant. But as far as my other equations go, here's what I would encourage you to do. When you read through this problem, something as complex as this, we're going to look at matching up units. And what I essentially mean is this. We said that our liquid portion of our diet is to provide at least 300 calories. Do we see this word calorie anywhere else? And so I see calorie here, I see calorie here, and I also see calories here. So reading through this again, we say I need at least 300 calories, but I know this. A cup of dietary drink X provides me 60 calories, and a cup of dietary drink Y provides me with 60 calories. So what we're going to do is we're going to come up with a calories equation. And that calories equation would say this. 60 for every cup of this plus 60 for every cup of this needs to be at least how much? And in this case, at least 300 calories. So we get 300. So now our next equation, when I look at this, I say vitamin A. And vitamin A occurs here, vitamin A occurs here, and vitamin A occurs down here. So I would say that this equation here, we'd say vit A. We have a vit A equation. We need at least 36 units here. So I would say 12 for every cup of X plus 6 for every cup of Y from our problem here. Add those together, we have to get at least 36 units, so 36. And then our last equation here is our vitamin C equation. When we talk about this vitamin C equation here, we need at least 90 units, and we get 10 from this for every cup of that, and 30 from every cup of this. So 10 from every cup of this plus 30 for every cup of this has to be at least, looks like 90 units of some vitamin C. So here's what we'll do. Let's go graph our feasible region. We need to talk about a scale to use here. Now I've only graphed the first quadrant, but the reason why is because I know that I'm going to get non-negative values in the first place. So in terms of scale, let's do this. Let's make our X and Y intercept charts here to find out where the X and Y intercepts would be on each of these graphs. We have X, Y, X, Y, X, Y. Since they're all in standard form, a little bit easier to just find a couple of intercepts on each graph. So for the first equation here, if we plug in 0 for X, I get 60Y equals 300. That just means that I'm going to get 5 for my Y value, and I'm also going to get 5 for my X value. So far, farthest we go out on each axis is 5. Now looking at the second equation, plug in 0 for X, and we get 6Y equals 36. So Y must be 6, but when we plug in 0 for Y, we get 12X equals 36, which means X must be 3. So now in this last equation, plugging in 0 for X, we get 30Y equals 90. So Y must be 3. And plugging in 0 for Y, we get 10x equals 90, which means X must be 9. I had to think about it for a second. So 9. So it looks like we have to go out 9 at the farthest. We say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just mark this with a 10. So we'll go up here. 1, 2, 3, 4. Try to evenly space here. Or if you have a grid paper, better yet, use your grid paper. So graphing all of our constraints here. I'm not going to graph x equals and y equals 0, but I am going to label those. I'm going to say y equals 0 and x equals 0. So now graphing our other constraints. I had one that had intercepts at 5, 0, and 0, 5. So we'll go ahead and to the best of my ability here, put in this. Now, use a straight edge. You want to make sure you use a straight edge. And I know you're probably rolling your eyes, but the reason why is because we're going to have to find some vertex values here, and they're not going to lie at nice, distinct points. So we'd say this next graph here had an intercept at 0, 6, so 0, 6, and 3, 0, which lies here. So we can see how this is going to cut down in here. We'll label this, and this was our 12x plus 6y equaling 36. And then our last equation had intercepts at 0, 3, so not quite as high as the other two on the y-axis, but clear out here at 9, 0. So what's going to happen is it's going to cut across here, like so. I'm going to label this one over here. We have 10x plus 30y equals 90. So now the interesting part about this is, of course, I know that this shades into the first quadrant because x is greater than or equal to 0, y is greater than or equal to 0. We have non-negative values. But the interesting thing is that if you plug 0, 0 into all of these equations right here, you get 0 on the left side of the inequalities, and you get all of these positive values on the right. So in either instance you look at, any of these instances, you get 0 is greater than or equal to some positive number, which is just false. So all of these constraints, these oblique constraints, they shade outward. And what that does is it gives us this unbounded feasible region that we're going to have to go and explore to find our vertex values here. So this cuts here, and then we have this last graph shading above. So all of this together, basically what we're going to do is we're going to have to find our vertices. Let me switch over to a bluey, bluey color. What I know is that the outline of my feasible region comes down along here and then must be bounded in and upward this way, and then it gets cut here by this constraint. So let me get that kind of out of the way there. And then goes down over here and then actually gets caught by the x-axis and heads outward. So our feasible region is this region out here, but in terms of vertices, vertex values, let's identify these here and how many we have. It looks like we have a vertex value here. Looks like we would have a vertex value at the intersection of these 2 points. Looks like we would have another vertex value here, and then the last one down here. So let's label the ones we know. I at least know this one was 9, 0, and I certainly know that this one right here, due to an intercept issue, not an issue, but just because I know, is right there. So to find these other 2 vertices, what we're going to have to do is, instead of eyeballing it, solve some systems to see where these intersect. So these 2 graphs right here, I'm going to go ahead and set up their system for this ordered pair. I know that it's the graph of, let's see, 12x plus 6y equals 36, and I'll keep this down here, and also the graph of 60x plus 60y equals 300. So if I write this, 60x plus 60y equals 300, you could see how solving this, I could take the top equation times a negative 10, and I would get negative 120x minus 60y equals negative 360, and adding this now to our second equation here, looks like we get 300. Looks like our y's cancel, and we get negative 60x's equals negative 60. So x must be 1 at that point. And if x is 1 here, we say go plug this back into one of these equations here. It certainly doesn't matter which. Maybe I'll put it into this one. I'll save myself some room here. 12 times 1 plus 6 times y equals 36. In other words, 12 plus 6y equals 36. So if I subtract 12 from both sides, I get 6y is 24, and I get y is 4. So our y value here must be 4. So now going for this other value right here, we say it's the intersection of 60x plus 60y equals 300. And this other graph right here that I labeled over here, I'm going to bring its equation over here, 10x plus 30y. The only reason I'm doing it right here is because I don't have room. If you have room on your paper, go do this somewhere else. But basically, I'm going to take this whole second equation times a negative 2, and I'm even going to displace it up over to here. If I take the second equation times a negative 2, I would get negative 20 x's, negative 60 y's, and I would get negative 180. So adding these up, I get 40 x's plus no y's is equal to, this would be 120. This means our x value here must be 3. And so our x value here being 3, if I plug that back into either of these original equations, maybe this one over here, I would say 10 times 3 plus 30 times y equals 90. So we'd have 30 plus 30y equals 90. In other words, 30y, subtracting 30 from our 90 gives us 60, so y must be 2. Okay, so all of this work just so we could get these vertex values. Let's go ahead and drop this into our objective function. So we say our vertices, we're going to list over here. We had 0, 6, and 9, 0 as intercepts down there. And then we were able to discover 1, 4, and also 3, 2. So essentially what we're going to do is go plug these all into our objective function, which is this 0.12x plus 0.15y. So I'm going to cheat a little bit on this video. And what I'm going to do is I'm going to head over to Desmos here, and we'll just set up an expression to put these in. So I only need the calculator portion of this. You guys can all look over here. But basically we have 0.12 times an x value. Let me get that out of there. We have 12 cents for every x plus 15 cents for every y. And what I'm going to do is I'll just copy and paste this in a few times here, and I'll go put in our vertex values. So we had as vertex values 0, 6, and 9, 0. So I'll put in 0, 6, 9, 0. We also had, respectively, 1, 4, and 3, 2. So here we go. We'll say 1, 4, 3, 2. So looking at all of these, we were trying to minimize our cost, and our minimum cost seems to occur when we have this 3, 2 pair right here. So I'm going to go put a little note around 3, 2. And as a matter of fact, you know what? Let's transplant our costs in here. We have 90 cents, $1.08. So we have 90 cents. Reacquire myself here. 90 cents. We have $1.08. I believe we had 72 cents, and we have 66 cents. So our conclusion statement is going to follow like this. We would say that the minimum cost is 66 cents, and it occurs when administering. And so in terms of X, we had 3 of our dietary cups of drink X there, and 2 cups of dietary drink Y. Administering 3 cups of dietary drink X and 2 cups of dietary. Cheers.